The differences in area for THW and THHW conductors between the 1999 National Electrical Code and the 2005 National Electrical Code stem from alterations in manufacturing processes. Specifically, the 1999 National Electrical Code conductors were produced using a method called annealing, while the 2005 National Electrical Code conductors were manufactured using a process known as cold working. Annealing is a heat treatment process that softens a metal and increases its ductility. This process typically resulted in conductors with a larger cross-sectional area. Conversely, cold working involves strengthening a metal through plastic deformation at a temperature below its recrystallization temperature. This process tends to produce conductors with a smaller cross-sectional area. The shift in manufacturing processes was motivated by the desire to enhance the electrical properties of the conductors. Annealed conductors generally exhibit a higher resistance compared to cold-worked conductors. Higher resistance leads to greater power loss within the conductors. Therefore, cold working was adopted to reduce resistance and minimize power loss. Furthermore, cold-worked conductors possess a higher tensile strength than annealed conductors. This increased tensile strength makes them more resistant to physical damage during installation and use. It's important to note that the change in conductor area does not affect the ampacity of the conductors. Ampacity, which refers to the current carrying capacity of a conductor, is primarily determined by two factors: the size of the conductor, typically expressed in American wire gauge or AUG, and the type of insulation used. The insulation material determines the maximum operating temperature of the conductor, which in turn affects its ampacity. The area of the conductor is primarily used for calculating the resistance of the conductor. Resistance is a measure of how much a conductor opposes the flow of electric current. The relationship between resistance, length, and area is defined by the formula resistance equals resistivity times length divided by area, where resistivity is a material property that indicates how strongly that material opposes the flow of electric current. Therefore, while the area of the conductor does play a role in determining its resistance, it does not directly dictate its ampacity. Ampacity is governed by the conductor size and insulation type, as specified in the National Electrical Code tables such as Table 310.15b16, which provides ampacity ratings for various conductor sizes and insulation types under specific conditions.